Hello everyone, in this video we're going to talk about a theorem known as the complex conjugates theorem. So this theorem is going to be very similar to another video we did on a separate theorem known as the irrational conjugates theorem, and I'll link that in the cards right now if you want to go check that out. So let's jump into the complex conjugates. So first of all, at the top we see what are complex conjugates, and it is a plus bi and a minus bi. So notice the difference there. We have one's plus and one's minus. And we have our imaginary number in there, bi. That's what makes it complex. Okay, so let's see what the theorem states. It says if f is a polynomial function with real coefficients, and a plus bi is an imaginary zero of f, then a minus bi is also a zero of f. So when we're looking at a problem, and like the example we're going to do in just a second, and it asks us to write a polynomial function, and it gives us a zero. And if it gives us an imaginary zero, we know that the conjugate of that would also be a zero. Okay, so we can do this in our example right here. It says write a polynomial function f of least degree that has rational coefficients, a leading coefficient of 1, and the zeros 5 and 1 plus I. So we can go ahead and write off f of x is equal to, and since we have a zero that is 5, we're going to write that as x minus 5 as a factor, because we know if we set that equal to 0, it would give us x is equal to 5. And so now we can write x minus 1 plus I. And since we're going to have some parentheses in there, let's write this in brackets. So 1 plus I in brackets. And then since we know 1 plus I is a 0, then also 1 minus I would also be a 0. So we could write this as x minus, and then now this would be 1 minus I as our other 0. Okay? So now what I'm going to do is use a property here that allows us to regroup our parentheses in our two terms that are in brackets. And so we're going to write f of x is equal to x minus 5. And now in brackets, I'm going to move my parentheses to be around x minus 1 plus I. And same thing here, x minus 1 minus I. So now what we've done is we've created the sum and difference pattern. So notice we have x minus 1 plus I times x minus 1 minus I. So once we have the sum and difference pattern, we can multiply that to give us the difference of two squares. So that's going to be x minus 1 quantity squared minus I squared. So now we can simplify what's in the brackets a little bit. We have the square of a binomial, so we can factor that as a perfect square trinomial. And we know that I squared would be negative 1. So we can do f of x is equal to x minus 5. And now in brackets, we're going to have x squared minus 2x and then plus 1. And then we'll have minus negative 1 on the outside. So we have minus there, and then I squared gives us a negative 1. So now we can simplify in our brackets one more step. So f of x is equal to x minus 5. And now we're going to have, actually we can write this without brackets now, x squared minus 2x, and then we have 1 minus negative 1, which would be 1 plus 1, so we get 2. All right, and so now we have x squared minus 2x plus 2, and now we can just multiply our binomial by our trinomial. So we're going to multiply x by all three of our terms. So we're going to say f of x is equal to x times x squared would be x cubed, x times negative 2x would be negative 2x squared, and x times 2 would be plus 2x. And then we're going to multiply negative 5 by all three of our terms. So negative 5 times x squared, negative 5x squared. Negative 5 times negative 2x plus 10x. And then negative 5 times 2, negative 10. Now all we got to do is combine our like terms, and we have reached our polynomial function of least degree. So we have x cubed, and then we have a negative 2x squared minus 5x squared, so negative 7x squared. 2x plus 10x, so plus 12x, and then minus 10. So our final polynomial of least degree that has rational coefficients, a leading coefficient of 1, and the zeros 5 and 1 plus I would be f of x is equal to x cubed minus 7x squared plus 12x minus 10. And that's how you can use the complex conjugates theorem.